So section 4.3 is going to discuss independence and conditional probabilities. We're going to start with the independence part and then work our way over to conditional probabilities. Those are going to be related to independence. So here we go. What's your idea of independence? What does it mean for two things to be independent? I mean, are you independent of your parents right now? I mean, you don't have to answer that to me, but what does it mean to be independent?
One doesn't affect the other?
Yeah, something doesn't affect the other one, okay? And in probability, when something is independent, then the two events, don't affect each other. So let me introduce you to some notation. P of A given B. So this is the probability of event A given that event B has occurred. So, if you know that this event occurred, how does that affect the probability of event B or event A? So we're going to spend some time on that. That's going to be related to calculating other probabilities, and it's also going to be wrapped up in something called independence. So let's take a look at this, and it's also going to bring back our 5% rule for us. So, in a study of college students' streaming habits, researchers found 46,637 students mainly watch shows on Netflix, while 111,874 mainly watched content on other platforms such as YouTube, TikTok, and Disney+. If one of these 159,511 students is randomly selected, what's the probability that the student mainly watched content on Netflix? So, okay, let's see. I'm just going to call this example A. Probability of watching Netflix. Watching Netflix. Okay. Well, we're just looking at one of these. I'll call this event N for notation purposes. What's the probability that we pick somebody at random from this study that watches Netflix? Well, there's 159,511 students in this study. 159, 511. How many of them watch content mainly on Netflix? Nice, 47,637. Okay. Now, we're going to expand on that. And we're going to use the idea of independence to help us out. If 5 students are randomly selected without replacement, what's the probability that all 5 students mainly watch Netflix? Well, maybe you remember from our work last week, what does it mean, or what kind of events do you get when you're sampling without replacement? Are you getting independent events or dependent events? Dependent events. Thank you. So if we're getting dependent events, and don't copy this down, please don't copy this down. Part B here is going to ask us for the probability that the first student watches Netflix and the second student watches Netflix, and all the way down to the 5th student watches Netflix. That probability, if you wanted to calculate it exactly, would look like this: 47,637 divided by 511. 511. And if we take one out of here, then we're also taking one out of this pool as well, so then there'd be 47,637 or 636 times 159,510. And you can kind of see what the rest of this would look like, right? It's just going to keep on decreasing by one, by one, by one. But that would be kind of a pain to have to put in your calculator, wouldn't it? I mean, I think most people would be unhappy. I wouldn't ask you to calculate something like that. So instead, let's notice the 5% rule. 5% rule, as a reminder, if your sample size is less than 5% of the population, then you can treat the samples as being independent. Treat the samples as being independent. And that does something wonderful for us in terms of calculating this probability. So this probability, well, let's verify that we're under the 5% rule. And I think that's pretty easy. So let's do 5% of 159,511. So 5% of 159,511, 0.05 times 159,511. And that's going to be probably like what, 750 maybe. Actually 7,500, 7,800-ish. It's going to be pretty big. Certainly, if we're only taking out 5 from this sample, then we're going to be less than that 5% threshold. But let's go through it anyways. Clear this out. 0.05 times 159,511. There you go. So we're clearly below the 5% threshold. So we can use the 5% rule. So that's going to mean P of N1 and N2 all the way down to N5. And by this I mean you're drawing out the first person who watches Netflix primarily, the second person, and all the way down to the fifth person. That probability is going to be calculated as a probability of N1 times probability of N2 all the way down to the probability of N5. And that 5 didn't show up too well here. My bad. Now that's going to make our life a lot easier. Let's find out how. N5. Yeah, still not there. So the probability that the first person watches Netflix is 47,637 over 159,511. But because we're treating them as independent, then we're just going to treat the next one as being the same. We're just going to say, you know, it's as if we didn't, or it's as if we replaced it, sampling with replacement. And so on, all the way down to, you know, 47,637, 159,511. Now even this looks like a real pain to calculate on your calculator. But what's the fast way to do this? What's the fast way to calculate this on your calculator? Yeah, to the power of 5. 637, 159,511 to the 5th power. And that's the big thing here, is that because these are independent, we can multiply their probabilities together to get this final answer. And that's good enough. A lot of times I prefer a fraction as an answer as opposed to a decimal. Because quite frankly, if you gave me a decimal answer for this, it would look an awful lot like the decimal answer for this, and I wouldn't know what you calculated. So I tend to prefer fractions as opposed to decimals. Whew. How are we looking on that first one? Okay. So the nice thing about independence is that you can turn the probability of a product, that is one event and another one, into the product of the probabilities. So that's what you get by independence. By independence. So that's nice. It's a good thing to have. Okay. We're also going to go back and take a look at the complementation rule. Any other thoughts or questions on example A here? Three girls. Find the probability that when a couple has 3 children, at least one of them is a girl. Assume that boys and girls are equally likely. So even though that's not exactly true, we'll use that for purposes of our calculation. So example B here. Now I want to draw out the sample space for you in terms of having 3 children. So you could have girl, 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 boy, girl, boy, girl, girl, boy, boy. And now I got to do the same thing here, except the first child could be a boy. So boy, 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 boy. And then these 4 are going to be the same here. Girl, 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 boy, boy, girl, and boy, and then boy. So this is our sample space. And there's a little twist in these things, or hint, that you can look out for that can make your life a little bit easier. If we were to calculate the probability that when a couple has 3 children, at least one of them is a girl, let's take a look at all those different probabilities that we'd have to calculate. Well, that's at least one of them is a girl. Here and here and here, here and here and here. Wow, that's like 7 different probabilities that you'd have to calculate. And that looks like kind of a bummer. But do you notice anything about this? What's the one thing that I didn't check off?
All boys.
All boys. So let's go back and think about the complementation rule. And again, the key thing for you to think about the complementation rule is this little phrase, at least one, or at most. That's a little bit of a hint for you in terms of what's coming your way. So let me remind you of the complementation rule. Probability of A is 1 minus the probability of A bar. Or the other way around, probability of A bar is 1 minus the probability of A. What's A bar? Does anyone remember what A bar is?
Was it all boys?
Yeah, it's just not A. You know, if A is rolling a 6, then not A is rolling anything but a 6. If A is tossing a heads, then not A is tossing a tails. So it's just the opposite. It's just everything but the event itself. So in our goal here is we're trying to find the probability of at least one girl, but how would you characterize this?
Okay, wait, so like wasn't the girl like A?
So if at least one girl, tell you what, let's take a look at it this way. So let's see. Let's see. 1, 2, 3. 1, 2, 3. So 0, 1, 2, 3, 4. You know what? I'm sorry. I'm thinking of something different here. All right, 0, 1, 2, or 3. That's all we really need here. there. So this is the number of girls. You could have 0, 1, 2, or 3. We want to know the probability of at least one girl, right? So what events should I circle here that represent at least one girl?
Can't you have all?
1, 2, or 3. So that's event A right here. This is A right here. What's that leave for not A? What's the event of not A?
0.
Yeah. So to calculate the probability of event A, you could calculate the probability of 1 girl, or 2 girls, or 3 girls, or you could say it's 1 minus the probability of all boys. What's the advantage of that? What's the advantage of going 1 minus the probability of all boys? How many ways can all boys happen? Just one way, right? So instead of having to calculate 7 probabilities, 3 here, 3 here, 1 here, we can just calculate 1 probability. And that's kind of nice. That's actually really handy. So let's do that. So if A is the event of at least one girl, then this is the event of no girls. This is A bar. Event of no girls. So our probability of A is going to be 1 minus the probability of A bar, which is a probability of a boy on the first one, and a boy on the second one, and a boy on the third one. Probability of all those 3 things. Let me pause here for a moment. Are we okay with this calculation? Probability of at least one girl is a probability 1 minus the probability of all boys. And probability of all boys means a boy on the first, boy on the second, boy on the third. That's where we're at. Peyton, comfortable with that? All right. Anna? Ryan? Okay. All right. Now there's a key thing that they said in here. Well, let's see. No, they didn't say it. We're going to assume. If you get a boy on the first one, are you more likely to get a boy on the second one? Generally speaking, they seem to be independent. I mean, at least for this class, they will be. There is recent evidence about some other things happening, but assume these are independent. And for us in this class, we're going to assume that these kind of things are independent. Assume to be independent. Okay. That means I can break this up into the probability of B1 times the probability of B2 times the probability of B3. And now we've got it down to a point where we can manage this. According to the problem itself, what's the probability of getting a boy? Or just think about it. What's the probability of getting a boy? Half. Awesome. Thank you. A half. So that's the first one. What's the probability of getting another boy? Kristen? What's the probability of getting a boy? Pardon? Yeah. Half again. And one more. Josh? Thank you. So this is 1/2 times 1/2 times 1/2. That's really 1 minus 1/2 to the third power. And if you did it out on a calculator or something like that, you're going to find that that probability is 7/8, which makes sense in another way. here's 8 things that can happen. The only way you're not going to get a girl, or at least one girl, is if you have all boys. So there's a 1 out of 8 chance you'll get all boys. 1 minus 1 out of 8 is 7/8. That kind of thing only works because these points are all equally likely. So be careful about using that approach to try and solve these kinds of things. Typically, you're going to be doing something like this. So to recap, as we're reading this, we see some of these words that say at least, or sometimes you'll see at most, etc. When you see those words, at least or at most, start thinking of the complementation rule. We realize that at least one girl really means 1 minus the probability of all boys. And probability of all boys, because that was independent, we could calculate it as a product of these probabilities, and then just do a little arithmetic to get our answer here. Nice, nice. Other thoughts or comments on that one? Chevelle? Some question? Go ahead. It's tricky stuff, so if you have one, help me out.
Nothing that I have now. I just noticed something that I need to go over.
Okay. Hannah?
I have a question. So you broke it up because it's independent, but could you still solve it just within the parentheses where, like, what's the difference with?
If this wasn't independent, then I'd have to be doing stuff like this. Then I'd have to adjust for, you know, the fact that, all right, we got one on the first one. How does it affect the probability of the next one? If these events weren't independent, then you'd have to do stuff like this, or worse. It kind of depends on the particular problem. Yeah. No, appreciate the question. All right, let's move on down to births in China. So, and I don't know when it ended. Hannah, did you ever find out when it ended? The one child per couple policy?
2015.
Yeah.
2015? Okay, so for the longest time, China had a 1 child per couple policy, and that led to a skew in the data. But the probability of a baby being born a boy was almost 55%. That probably led to an imbalance. Means it's a lot more guys than girls, and I'm sure that created some problems socially, etc. Amongst 6 randomly selected births in China, what's the probability that at least one of them is a girl? So, all right. So this is still example B. It's just a different part of example B. Yeah, let's see. Example B, part 2. All right, we want the probability of at least one of them is a girl. So, Sophia, is there a word in here that kind of catches your attention?
At least one.
At least one. All right, so where did that go? At least one. All right, so that right there kind of hints towards using the complementation rule and eventually independence. So let's take a look at the event of at least one is a girl. A. At least one is a girl. Okay. And I'm going to do kind of what I did with the last one. And then as we're going to look at the different possibilities in terms of number of girls. So you could get 0, 1, 2, 3, 4, 5, or 6. Those are the numbers of girls that you could get. What I want you to do is I want you to circle all the events that constitute at least one girl. So circle on your own little number line all the events that constitute at least one girl. Are you agreeing with your neighbor? you have the same one circled?
Oh, I see.
All right. So what should I circle? What should I circle here that represents at least one girl? All of this, 1 to 6. So all of this 1 to 6, that's event A. In words, what does A bar mean? What does A bar mean? 0. All right, so A bar is going to be no girls. So that will circle here. This is event A bar. After we do section 5.2, the calculation of these probabilities is going to get a lot easier, but it's still going to be a pain. And you would have to calculate 6 probabilities to get the probability of A. You'd have to have the probability of this plus the probability of this, all the way through to 6. So calculating the probability directly is kind of a pain. Probability of A. So what else could I do other than using the probability of A? Be a heroine or hero. Come on, what do we got? What can we do to calculate this in a different way? Yeah, 1 minus probability of not A. What's the advantage of using the probability of not A? Yeah, there's only one thing to calculate, right? And that would be the probability of all boys. So that's going to equal 1 minus the probability of a boy on the first one, and a boy on the second one, and all the way down to a boy on the 6th one. Nice. Presumably, this would be sampling without replacement, which makes it dependent events. So at this point, I'd have to go, oh man, I really got to think a little bit. But there's something that saves us. I'm not sure if you're aware of it, but the population of China is about 1.3 billion. I don't think I need to calculate 5% of 1.3 billion to realize that 6 probably satisfies the 5% rule. All right, let's just kind of assume that that's true. So by the 5% rule, the 5% rule, these events can be treated as if they were independent. Okay. All right, so that's going to equal, if these are independent, then that probability becomes probability of boy on the first times probability of boy on the second, all the way down to probability of boy on the 6th. Okay. So I'm just going to put that in brackets there. Can anyone look at the problem and tell me what that probability is? Sunardita? What we got there? You can look back at the problem. Probability of a boy is 0.545. 545. That's the first one is a boy. How about the probability that the second one's a boy? Same thing. 0.545. 0.545. And, you know, kind of like the previous one like this, I don't think I want to calculate this 6 times. So the faster way to do this is 1 minus the probability of 0.0545 raised to the 6th power. So, okay. Oops, sorry about that. There we go. Not so bad. Let's take a look at this. 1 minus 0.545 raised to the 6th power. Bam. About 97.38. We'll call it. We'll round it to the nearest 10,000. 0.9738. Nice. Okay. Pretty good. Pretty good. Is that one feeling a little bit better? Starting to get a little familiarity there?
Yeah.
All right. All right. Let's do one last one by way of practice on this kind of stuff. Then we're going to start turning our attention to independence a little bit more and calculating conditional probabilities. If you make 10 random guesses for 10, or if you make random guesses for 10 multiple choice SAT questions, each with 5 possible answers, what's the probability of getting at least one correct? If these questions are part of a practice test and the instructor says you must get at least one correct answer before continuing, is there a good chance you'll continue? Well, let's find out here. So, example C, and I'll let it out, part 3. Actually, example B still. Again, there should be a little phrase in here that catches your attention. At least, all right? So when you see at least or at most, then you know, okay, I want to think of the complementation rule. So at least one. All right, at least one. Let's take a look at the number correct that you can get on an SAT test when you're taking a look at 10 questions. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So if event A equals at least one correct, then I should be circling all these events. That's the event of at least one. And then there's this guy. Mariana. How would you describe this? What should I write there for the notation for this? Yeah, A bar. There's A bar. Thank you. And basically that's none correct. No correct answers. So in trying to find the probability of at least one correct, all right, well, probability of A is going to be 1 minus probability of A bar. Now, they didn't really tell us too much other than that there's one correct answer out of 5 possibilities, but I think that's going to be good enough. So the probability of A bar, and I guess we're going to need to develop some notation for this. What do you want to use to denote a correct answer? What do you want to use to denote an incorrect answer? And just do C for correct, and then C bar for incorrect. So let's see. Let's C1 be the event. The first guess is correct. And then you can have C2 be the event the second guess is correct. And so on. So if C1 is the event that the first guess is correct, What's C bar? What's that going to mean? Yeah, first guess is incorrect. The event that the first guess is incorrect. And so on. C bar 2. And I'm trying to be explicit about my notation so you can follow along here. But this event here, the probability of A bar, that's going to mean the probability of C bar 1, C bar 2, C bar 3, etc., all the way down. So calculation of our probability, 1 minus A bar is going to be the probability of C bar 1 and C bar 2, and so on, all the way down to C bar 10. You're guessing all of these wrong. Bad luck on you. All right. Now we got to think through about something carefully. If you guess wrong on the first one, does that change your probability of guessing wrong on the second one? Or the third one? No. So these are independent events. Guessing wrong on one doesn't change your probability of guessing right or wrong on the next one. So these are independent events. And so that probability can be turned into the probability of a product. So that's going to equal 1 minus the probability of C bar 1 times the probability of C bar 2, all the way down the probability of C bar 10. There's an added bonus for you in this problem that we get to use the complementation rule once again. I'll let you work on that for a second. Let's figure out the probability that the person guesses wrong. Let's just look at one question now. How many possible answers are there for one question on the SATs? 5. How many wrong answers are there? 4. I hope this is a most 4. If there was 5, then it would be kind of a bummer. It would feel rigged. Let's see. So the probability that they guess wrong would be what? 4 out of 5. And then it's going to be the same probability for the next one. 4 out of 5. How are we going to put that in our calculators? Suggestion? Mark?
10. 4 to 5 to the 10.
Yeah, 1 minus 4 out of 5 to the 10th power. And if you don't like fractions, 4 out of 5 is 0.8. You can put it in that way as well. So let's give this a shot and see what we get. Let's see, come on. So 1 minus 0.8 raised to the 10th. Think there's a good probability that this person is going to move on to the next phase? What do you think? Is there a good chance you move on to the next phase? Yeah, it's almost a 90% chance. So about 89.26. 0.8926. Yeah, there's a good chance you're moving on. Okay, so we're feeling a little bit better about these independence problems and calculations based on those things. Let's dive into independence a little bit more. Move down to example C here. This is kind of an interesting study. It's about delayed gratification and what it reveals about people if they're willing to wait for something, basically to earn it. Now, in this study, you had students that had a choice, or that were given, sorry, I don't think they had a choice here. They had a choice here. They were given either 4 quarters or $1. Now, they were then offered the chance to purchase gum or just keep the money. And let's take a look at some of the resulting probabilities. So first of all, find the probability of selecting someone at random who spent the money. Let's put in some marginal totals for ourselves here and try and understand something about ourselves in the process. So let's see, that's going to be 43 and 46 for a total of 89. Let's try it this way. That's going to be 39 plus, and that's not 189, that's just a little box there. 39 plus 50, 89. So both of those totals add up to 89, feeling pretty good. What's the probability of selecting somebody at random who spent the money? Well, how many people spent the money? What column should I look at for spent the money? Yeah, purchase gum. So you got 39 out of 89. And let's see what percentage that is. Guessing about 44%-ish. 39 divided by 89. Yeah, pretty close to 44%. So about 0.4382. Okay, but here's where we're going to start working with our conditional probabilities. Find the probability of selecting somebody at random who spent the money given that they received 4 quarters. So probability that they probability of spent given they got 4 quarters. This changes the sample space. You're telling somebody in advance that, okay, let's just look at the people who got 4 quarters. So if we're looking at the students who got 4 quarters, then this is our sample space right here. It's no longer the whole table, it's just this right there. The ones who got the 4 quarters. You're not looking at 89 people anymore. How many are we looking at? 43. Of those 43, what's the probability that you spent the 4 quarters? 27 over 43. Now, I was never very good at math, but I'm thinking that that's different than the 44% we got for the last one. Let's check it out. So 27 divided by 43. Wow, now about a 63%. Okay. Let's try this again. So at this time, find the probability of selecting somebody at random who spent the money given that they received $1. Okay. So they got a dollar bill. Is that a little stickier in their wallet? Were people less likely to spend it? Let's find out. So this time we're looking at the probability of spending it given they got a dollar bill. So again, you've changed the sample space. The sample space is all the things that can occur. But when I'm telling you somebody got a dollar bill, we're no longer looking at all 89 subjects in this study. How many people are we looking at? 46. All right, so we're looking here. 46 people. Of those 46, how many of them spent the dollar? 12. 12 over 46. So again, let's calculate some probabilities here. 12 divided by 46, 26%. So, wow. Now both sets of students got $1, right? Did the form of that dollar change their spending habits? Yeah. It's a lot easier to, shell out a few quarters as opposed to a dollar bill. I don't know. Do you experience the same thing? Every now and then when I'm, flush, I got a 50 or even 100 in my wallet. Man, that doesn't come out of there very easily. You look at that packet of gum or that candy bar and you're like, nah, I don't need it. You don't feel like busting up that 100. But if you had a 5 or a single or something like that, yeah, sure, why not? You got a couple singles, they come out really easy. So the big question then is, are these events independent? Is the currency you got, does that change your spending habits? Absolutely. Look, I mean, as a whole, 44% of people spent the money. But if you look at people who got the quarters, they're much more likely to spend the money than if you got a dollar bill. This information certainly changes that probability. And if that happens, then yeah, these events are independent. Or excuse me, these events are dependent. So, let's see. Do the results of domination receive purchasing government, are they independent? Yes. The people who got 4 quarters were much more likely to spend the money. Yeah, the probability of spending that money changed based on what denomination you were given. So absolutely. Absolutely, did make a big difference there. Okay. Comments or follow-ups on this one? This is a good but sticky part of the course. People struggle here. I get it. I understand it. So if you need or want some help here, please point to something and say, whoa, wait a minute.
I have a question.
Yeah, thank you. What's up?
Why is it not dependent on the denomination fees if it changed when they got 4 quarters versus $1?
Let's see. Did I write this right? Let's see. The results. Oh, should be. I was answering dependent. My bad. No, they're dependent. So yeah, should have wrote a no there. Awesome. Thank you. Okay, let's look at the next one down here. Example F.
Sorry, real quick, we have a question.
Oh, another one.
So wait, why
Hannah,
is it
please.
no?
What's that?
For G, why is it no? It's no because
Are they independent? No, they're not they're not independent
oh, okay.
because if you got 4 quarters, you're more likely. It changes your probability of wanting to spend it. If you got $1, you're like, nah, I think I'll keep that. But if you got 4 quarters, like, who cares? A couple quarters doesn't matter as much. So it changes the probability.
I keep getting independent and dependent mixed up. So.
Well, and then there's mutually exclusive as well. So there's a lot to keep track of. Let's do our best. And it's going to continue with this one. We're going to flip a couple coins. We're going to bring back our nice $1972 silver dollars. So there's a total of 4 possible things that can happen when you flip a couple coins. So here they all are. What's this S stand for here? Sample space. This is the space that all things that can happen when you flip 2 coins. Now you can look at it in terms of this, your sample space here, or you can draw a tree diagram. So that's okay as well. But either way, let's look at a couple things. let's look at the probability of a head on the second flip. You're going to flip 2 coins. These are all the things that can happen. What's the probability of a head on the second flip? Well, all 4 points in here are equally likely. So if they're all equally likely, what's the probability of getting a head on the second flip? And give it to me unreduced, please, if you could.
Are you finding heads on the second?
Heads on the second flip.
1, 4.
Well, let's take a look here. How many ways are there? Well, first of all, how many points in my sample space do I have? 4. How many ways do I get a head on the second flip? There's 2 different ways I can get a head on the second flip, right? Which reduces to 1/2. Now let's play a different game. Come on, cooperate. There we go. I'm going to flip 2 coins, except before I flip the second one, I'm going to tell you, psst, I got a head on the first flip. How does that affect the probability of a head on the second flip? Well, let's find out. If you got a head on the first flip, keep in mind that that's what this is saying here. Let me just write that out. Probability of a head on the second flip given a head on the first flip. That's what you're trying to find. So, our sample space is no longer all 4 of these things, right? We only want to choose the ones that had a head on the first flip. So our head on the first flip. Try and look at our little sample space there and just pull off the parts that have a head on the first flip. What should I be circling? If I'm going to circle in blue so you can kind of correlate, your new sample space with this, what should I be circling? Yeah, these 2. Thank you. That's your new sample space. Okay. Of this sample space, what's your probability of getting a head on the second flip given that you got a head on the first flip? Well, that's our new sample space. How many events are there in this sample space? Rukiah? 2. So 2 events. How many of them have a head on the second flip?
1.
Just 1, right? So did the information that we had a head on the second flip change the probability of getting a head on the first flip? No, they're the same. So does that mean these events are dependent or independent? Independent. And that makes sense, right? The coin doesn't have a little memory chip in it or doesn't have, some communication with this other coin to say, oh, well, you came up with the heads, I should come up with the heads too, or something like that. All right, these are independent. What happens with this flip doesn't affect the probability of what happens with this flip. They're just independent. And that's something I mentioned the other day. It's the gambler's ruin. A lot of people, when they gamble, they think something's due. Oh, no, I've been at this slot machine for hours. It's due. It's got to hit. No, it really doesn't. You could be pulling out that thing till the cows come home, and it's still not going to change your probability. They're independent events. And those things are really well regulated if somebody wants to stay in business as a casino. It's just that the reason they make money is because they don't pay you out the odds that you should get if you're getting paid the true odds. Okay. So this is a good example. These are independent events because the outcome of one does not affect the probability of the outcome of the other one. It was 1/2 here. It's still 1/2 knowing that you got ahead on the first flip. Doesn't change. Okay. So let's go back over this notation a little bit. Probability of H2 given H1. This is what happened. This is the probability, or this is the event you're looking for. Its probability given that this happened. So see if you can't put into words this probability down here. Event A is the subject is telling the truth, and event B is the polygraph indicates that the subject is lying. So choose the correct verbal statement that corresponds to this event, or this probability. Probability of B given A. Put that into words. If you're watching this later, then pause the video and try and choose the correct one. Okay. Check with the neighbor. Do you agree?
Yeah, fair enough. I think the reason why I just did D because I just took it like word for word, like given the automatic just crossed out true for me. I think so.
Are you already checked? Okay. All right.
Yeah.
Jamia? You need a neighbor? Okay. Okay. All right. Okay. Okay. Let's understand what this is in terms of the given. What's given in this problem?
The subject is telling the truth.
Yeah, subject. Thanks, Frederick. Subject is telling the truth. All right. And then what's the probability we're looking for? What's the event we're looking to see happen? Indicates it's lying. All right. Polygraph says nuh-uh. Okay. So let's see. Polygraph indicates that this subject is truthfulness. Well, we can kind of stop right there, right? And indicate they're being truthful. In fact, we can get rid of both of these two, right? So the polygraph indicates the subject is lying. Given that the subject is actually lying. Well, that's not right. So it's the last one, right? D. Nice. Okay. Let's do one last one real quick in terms of our independence and things like that. If 3 smartphone users are randomly selected, what's the probability that at least one of them uses two-factor authentication? All right, well, we've got the results of this survey that says 70% use two-factor authentication. So 3 smartphone users, at least one. That should be jumping out at you. At least one. Has everyone heard of Pavlov's dog? It's supposed to be this automatic reaction, right? They ring the bell, you start getting hungry, salivating, etc. When you see at least one, you start thinking of the complementation rule. So, probability of at least one is going to equal 1 minus the probability that none use two-factor authentication. Since we're dealing with 3 smartphone users, probability that the first one doesn't use, and the second one doesn't use, and the third one doesn't use. So here I'm using D1. First one doesn't use authentication, second one, third one, etc. Now, typically speaking, these surveys are done without replacement. Never seen a survey where people say, oh, well, let's just put them back in the pool and maybe sample them again, maybe not. So if you're sampling without replacement, then technically these would be dependent events. But chances are 3 is going to be much less than 5% of your sample size. So by the 5% rule, we can assume independence. So it's going to be 1 minus probability of D1 times probability of D2 times probability of D3. There is one more little thing that we're going to have to work around. 70% of users use 2FA. Well, what percent don't use 2FA? 30%. So it's going to be 1 minus 0.3 times 0.3 times 0.3. So 1 minus 0.3 to the third power. I don't know. Oops. That should be 0.027 maybe. So 97.3%. I don't know. We'll find out. 1 minus 0.3 raised to the third power. There we go. Nice. 97.3%. One last reminder here of some stuff. It says, how would the results be affected if the participants were people who voluntarily responded to a cybersecurity poll posted on Reddit or X? What would be the problem there? Yeah, you're going to be skewed, all right? Voluntary response, that's going to skew the results. It's just going to be a biased poll. Really, no amount of statistical torturing is really going to make that anything other than just a reflection of the people who happened to see it and chose to respond. You won't be able to generalize that result. Okay, let's take a break.